Now the next talk is by Svitlana Kondovych, will be some follow-up of parts of the previous talks, which is a Cairo breakdown of the domain wall dynamics in biaxial magnetic nanotubes. So please, Svitlana, go ahead.
Hello, everyone. I'm really glad to be here today and that this workshop is happening. And I want to thank everyone who made it possible. And as Flavio said, my talk is a follow-up of the previous talk. So I will tell you about our work on chiral breakdown in domain wall dynamics in biaxial magnetic nanotubes. The work was done in collaboration with Denis Sheka, the previous speaker, and Kostya Yershov from RW. And this is a particular case of how the interplay of curvature, Delshinsky-Maria interaction, and magnetostatics creates a particular setup for domain wall statics and dynamics. So this is a brief outline. First, I will explain what exactly, which models I use in this work. And then I will explain how chiral breakdown appears. Well, there is a spoiler. It appears as a result of combined action of bulk type DMI and curvature in magnetic nanotubes. And then I consider magnetic nanotubes with another type of intrinsic DMI interaction and discuss how magnetostatics adds to the whole setup. So in the previous talk, you've seen a lot of beautiful pictures of curvilinear systems. And I hope you got convinced that they're worth considering. However, this is my favorite pictures from this work, because it nicely summarizes how curvature shows up through local and non-local interaction in both anisotropy and chiral interactions in the materials. So here you see beautiful examples of different systems of various geometries. However, the most common playground for these systems, I guess, is magnetic nanotubes, because it's comparatively easy to fabricate and study. This is constant curvature systems, and many interesting effects have been observed in recent years. As an example, there is a dependence of domain velocity on applied magnetic field in nanotubes with intrinsic DMI. And as was mentioned in the previous talk, there was also chiral breakdown seen in systems without intrinsic DMI, but with magnetostatic interactions, which created interesting dynamic effects. The system I will tell you about was considered in this work, and this is the magnetic nanotube with a particular anisotropy. So you see this biaxial anisotropy is characterized by anisotropy ratio, which includes easy surface anisotropy and easy axis anisotropy tangential to nanotubes surface. So the ground state of such a system would be the vortex state of magnetization, tangential to the surface. However, if the system also features Delshinsky-Maria interaction of bulk type, the ground magnetization state tilts from this E1 direction by a small angle proportional to the strength of the DMI interaction and the curvature of the system. So the interactions we consider in such a system is anisotropic energy, exchange energy, Delshinsky-Maria interaction, and magnetostatic interaction. So what we see, the profile of the domain wall is in such system can be characterized in these angular variables by this ansatz, which includes the domain wall width and topological charge of the domain wall. And in the ground state, it is characterized by a certain helicity. So here you see the analytics and also micromagnetic modeling of the profile of the domain wall in such a system. which is obtained by minimization of the energy of such a domain wall. You see here the dependence on three effective parameters, effective anisotropies and effective mesoscale DMI constant, which all depend on the curvature of the system, on the strength of DMI, and on the anisotropy. In this particular system, we estimated that dipole-dipole interactions do not add much. It just they show up by a shift of anisotropy in the system, which we take account of by renormalizing the anisotropy ratio epsilon. So these are equilibrium parameters of such domain walls, domain wall width, and the equilibrium phase. You see they depend on the same parameters. So as I said, as I have shown in the previous slide, it's curvature, DMI, and anisotropy. The chirality of the resulting domain wall depends on three parameters, which is topological charge, helicity, and the sign of the DMI interaction. Here you see the profiles of two domain walls of different chiralities. So if the product of these three components is less than 0, we have one chirality of the domain wall, and if it's positive, we have another chirality. So next step is to see what happens with these domain walls in the external magnetic field. So first we consider the vortex magnetic field. So the direction of magnetic field you see here shown with these small hand icons. So we have two domain walls with the same sign of DMI, same topological charge. They differ by this helicity C. So when these domain walls are affected by the external magnetic field, three different situations can occur. So below some critical field, which is called chiral field, the two domain walls move, and the domain wall with the non-favorable helicity, non-favorable chirality, moves at a smaller average velocity than the favorable domain wall. At the critical value of the magnetic field, the so-called chiral breakdown occurs, and in between two critical fields, chiral field and Walker breakdown field, the chirality switching for the non-favorable domain wall can occur. So in this case, system first, the domain wall first moves at the constant velocity, then it undergoes a transient stage during which the chirality switches, and then it continues moving. So it switches chirality, so it behaves like the favorable domain wall up until reaching the Walker breakdown field. So all these all critical fields depend again on the anisotropy, curvature, and DMI. So here are some snapshots of the position of domain wall with time. So you see for the favorable domain wall, it moves on the constant with the constant velocity, but the unfavorable domain wall undergoes, so this is a snapshot of the initial position, of the initial chirality of the domain wall. Then it undergoes the transient stage with the creation of vortex-anti-vortex pair, and then annihilation of this pair, and then it switches chirality and behaves like a favorable domain wall. So Kostya created a nice video of this switching. Let's see if we can show this video. Yes, I don't know. Okay, so you see here, so the favorable domain wall is pretty boring. It's just moving and nothing happens, but unfavorable domain wall, you see it, so this is the first stage where it moves. You can also see here the parameters that were used for modeling. And now you see, so you see this part enlarged here. And this is the unrolled tube where you see the creation of vortex-anti-vortex domain, vortex-anti-vortex pair, and then the domain wall switches the chirality to the opposite one. So, and then it settles down and moves on the constant velocity. Let's go. So another situation to consider is the case of axial magnetic field. Since the ground state of magnetization is tilted with respect to ground state, it's also possible that it interacts with axial magnetic field. But in this case, we observe no chiral effects. The topological charge defines the direction of the movement of the domain wall, and we see it is proportional to the magnetic to the DMI and curvature of the system. So it simply defines the direction of the motion, and it is possible to have this constant velocity because of the interplay of bulk DMI and curvature in the system. And the last part of the work was devoted to another type of DMI, intrinsic DMI. So if we consider DMI of this type, which actually prefers also the tangential orientation of the magnetization on the nanotube surface, the situation changes, of course. So first, the profile of the main wall is different. There appears this phase slope, which you see here because of the change in sign of radial component of magnetization. So there is no tilt of the ground state, and so the geometry of the domain walls is defined by the sign of the Zaleshinsky-Murray interaction. So with this ansatz, we minimize the energy of such domain wall. We see also the parameters, the anisotropy and the effective anisotropy and DMI of the system depend on curvature and DMI, same as in the bulk type DMI situation. Also, magnetostatic rescales the anisotropy of the system. However, in this case, dipole-dipole interaction also adds to the equilibrium value of the space slope. In fact, it is not a chiral effect, so magnetostatic does not generate any chiral effects in these situations. However, so this phase slope remains the same for the domain walls of any chirality. So the sign or the preferable sign of the phase slope is actually positive, and depending on the sign of DMI and magnetostatic can either compete or work together on the value of the phase slope. So this is just interesting deformation of domain profile. However, chiral effects are not expected. As for the domain wall motion in this case, we consider just the case of the vortex magnetic field, while we have no tilt in the ground state, and we see that the Walker breakdown field shifts also with respect to the non-DMI value. So the shift is also proportional to the DMI and to the curvature in the system. What this effect is much smaller compared to the bulk type case, and also the contribution of local and non-local interactions are really small compared to this shift of the Walker field. So the outcome we can get is to shift a Walker field a bit to extend the range of possible fields to tune the motion of the domain wall, same as in the bulk type case. However, no switching or so this is the only feature of the domain motion in this case. So the summary is that in magnetic nanotubes for biaxial anisotropy, we observe effects in case of bulk time, the intrinsic DMI, which are chirality symmetry breaking in vortex magnetic field or translational motion in the axial magnetic field. As for the interfacial type DMI, we see the asymmetric slope in the domain wall profile. And for both types of DMI, we observe a linear shift in the critical wall breakdown field. Thank you for your attention.
Thank you, Svitlana, for this nice talk and for staying time. That's, so, any questions from the audience first?
Yeah, just maybe a question. You always telling about this ferromagnetic order when you consider this effect. Will it be the same for antiferromagnetic, or why you do not say about antiferromagnetic ordering in your systems on the surface?
Well, so we didn't investigate antiferromagnetic order, so it can be done also. So since
will it be the same skyrmions, vortices for antiferromagnetic order?
Well, we consider just domain walls. So I guess there is a really nice work of Kostya and Vladimir Kravchuk on skyrmions on Earth surfaces. And I guess there is an interplay between antiferromagnetic skyrmions, different types of DMI with curvature too. So for domain walls, we didn't investigate this.
So further questions from the audience over there?
Thanks. Maybe more general question. How do you imagine the fabrication of the structure? Because with interfacial Dresden-Moria interaction, it's no problem. It's just a bilayer system, yes, for magnetic heavy metal. But for bulk DMI, if I know that it requires single crystal material, if it is, what is the feasibility of this?
Yeah, this is a really good question. I think it's being done, so it's possible. Systems like that are fabricated. But frankly speaking, I cannot give you much detail on the fabrication of nanotubes. So
let's go to online question now. If there is time left, I can ask further questions. So Volodymyr asks.
Hello, everyone. Hello, Svitlana. Thank you for a very nice talk. My question is about the relation of your work and the work of Ricardo Hertel, who noted the presence of preferable chirality for domain wall, for moving domain wall on a tube. And Ricardo explained this effect by dipole-dipole interactions. So in your system, you said that dipole-dipole interaction does not play a big role. So the question is where this effect of preferable chirality comes into your system.
Hello, Vladimir. Thank you for your question. So in our system, chiral breakdown originates from the Lushinsky-Maria interaction. So for the work of Hertel, which I showed in the introduction, indeed, this chiral breakdown originates from magnetostatic interaction. However, the geometry of the system and the profile of the domain wall, so they have this head-to-head or tail-to-tail domain walls. And there, the radial component inside the main wall interacts differently with the magnetic field. That's why the chiral breakdown occurs. However, the symmetry of our domain wall does not allow this kind of chiral effect. So you have parity of the magnetization components. So the magnetostatic effects, the chiral magnetostatic effects, does not. So in our case, the similar chiral breakdown as observed by Hertel is generated by the DMI.
So we have time for one quick question, please.
Yes, one more general question. As far as I understand, curve geometry can lead to changes to correlation and crystal anisotropy. Is it possible to choose some special curve geometry to fully compensate crystal anisotropy?
Fully compensate crystal anisotropy. Oh, well, actually, the idea was to make our system anisotropic, to have a particular type of the domain wall. So we could, so there is a contribution to anisotropy from the curvature, that's for sure. So most likely you can adjust the parameters to fully compensate. However, I think you can start with the isotropic system then. So
Okay. Okay, thank you.
Okay, let's take also a speaker again.